Right, so, no, excellent. Alright, so some of you know Regina, some of you don't. My plan is just to give you a bit of a tour through what it does, and for those of you who know it, show you a little bit of what's new. So Regina is software that's doing 3-manifold triangulations originally, nowadays 4-manifolds, D-manifolds. Really recently, like this was all pushed to the main repository yesterday, not some links, native not some links. But anyway, so let's move on. So what does it do? So the main philosophy behind Regina, you look at programs like Snappy. Snappy is looking at hyperbolic manifolds, and the focus of Snappy is the manifold. Right? So in a sense, the focus of Regina is looking at 3 manifolds, but it's the triangulation. So Regina is particularly good at things that wrangle triangulations, things that analyze the combinatorics, the algebra of the triangulations, and somehow that's the first-class data structure. What kinds of things would you want to do with Regina? So essentially anything that's not hyperbolic. If it's hyperbolic, you give it to these two. If it's not, then maybe Regina will help. So things it does very well are things like 3-sphere recognition, line-rate recognition, testing Harkenness, so looking for essential surfaces inside your manifold. So these are things that you just have buttons that will do, right? And the buttons work fast enough for triangulations that are reasonable enough. Things that it sort of does well, so if you want to do things like, well, it'll do prime decomposition, so you give it a manifold and it will split it into prime pieces. Things like JSJ decomposition, it gives you some of the primitives, so it will look for embedded surfaces, it will cut along them, you can analyze them yourself, and so somehow it doesn't do these decompositions, but it gives you the native tools that you need to do it yourself. Other things that it sort of does well are things like recognition problems, so you just give me a triangulation and say, what's the manifold? So of course it will not solve this problem in general all of the time, but it can solve it certainly some of the time. Sometimes by looking at the triangulation and seeing the manifold, sometimes by doing some of these decompositions, some of them by looking up the census databases which it has buried under the hood. But the general idea of Regina, I mean in a sense also, if you want to distinguish between what's going on with Regina versus what's going on with Snappy, Snappy is doing very fancy stuff using numerical techniques and other things, but it's somehow at the core you've got looking for solutions to Thurston's Billinger equations. Regina is coming from the other direction. It's using discrete techniques essentially for everything. So one of the advantages of that is that your results are exact. So it will, if there is a possibility that your integers will get bigger than 64 bits, it will use arbitrary precision arithmetic. It will, if it gives you an answer, promise that it's the right answer, although of course maybe it's too slow and it doesn't give you an answer at all, or maybe it just comes back and says, I don't know. But the idea is that when it gives you an answer back, you should be able to trust it. So these are useful in particular for things like computer proofs and certificates of, computational certificates of whatever properties. Alright, how old is Regina? It's 18 now. Somebody told me yesterday that it can vote. Excellent. In Australia it can drink. Anyway, it's got 360,000 lines of source code, plus it's also got embedded in it the Snappy kernel, so if you want to pop out and do some hyperbolic geometry, instead of having to work back and forth between 2 pieces of software, if what you want to do is simple enough, it buries the Snappy core inside it, so you can do simple things, get a geometric structure, look at the volume. If you want to do anything a little bit more sophisticated, you give it to Snappy. But it's there if you need it. The normalist kernel, which is doing essentially Hilbert bases on polyhedral cones, it's using that actually as part of one of its core algorithms for enumerating fundamental normal surfaces, which is somehow a much harder problem than vertex normal surfaces. It's had a lot of releases. It's open source. If you want to know what the asterisk is, come back and talk to me. But without the asterisk, you can't put GPL software on that device there because Apple doesn't let you redistribute without constraints. But anyway, that's another story for another time. Contributions are welcome. If you would like to contribute to Regina, please talk to me. More importantly, by the way, if you're interested in packaging Regina, this is a small nightmare, and if you run Windows, it's a freaking major nightmare. So if you're interested in helping with packaging Regina when a release comes out, so people can just install it out of the box and run it, please, please, please talk to me, because I would be very happy for that help. It's not a one-person project, so there's lots of people who have contributed patches. Ryan Budney and William Pedersen in particular have contributed a lot of code. If you want to talk to Will, he's in Glasgow. Now, he's on this continent. Well, this isn't a continent, I guess. He's on this island. So he moved there to take up a postdoc very recently. And
where's Ryan?
Ryan is, to the best of my knowledge, still at UVic in Canada. So what's the philosophy behind the way Regina is written? Mark actually answered this question for me a couple of days ago, but the general idea is this: the first priority is that the code should be correct. Right? You have it correct, then you need to make it general, so that it doesn't only work for your particular problem that is good for your particular paper. The point is that you have an algorithm that can be used widely for all sorts of inputs. Right? So Regina tries to be as general as it can, and then within those constraints it tries to be as fast as it can. So that is the order of priority. In the interest of keeping things correct and at least giving you more confidence that it's correct, there is an enormous test suite, 26,000 lines of tests that you can run. You can do it on the iPad too, but it will take 5 minutes, so I won't do it now. But it's just to verify that the machine is doing what the machine is supposed to be doing. So where you use it, computer proofs, experimentation, computer assisted proofs, where you need to find some gadgets that are in a theoretical argument, but you need the machine to help you find just the right gadgets, just the right property. So we used this in an NP completeness proof a few years ago to find exactly the right gadgets to hook up three-manifold problems with satisfiability. It runs on an iPad, it runs on your desktop, it runs on supercomputers, so you can put it doesn't run on this. Anyway, but you can more or less put it wherever you like to use it. I've talked a bit about what it does, but really the big things again are the combinatorics of triangulations, normal surface theory and angle structures. It's used for census enumeration, it does algebraic invariance, it talks to Snappy. If you have Snappy installed and you use the Python interface for Regina, you should be able to just say import Snappy and it should just work. And if it doesn't, talk to us while all of us are here and we can try and fix that. It's got a GUI, a graphical user interface for the normal people. It's got Python bindings for the hardcore people, and the bulk of the code is written in C++, so if you really like fighting with template metaprogramming, you've got all the C++ under the hood. It's very thoroughly documented, so all of the functions and classes... Sorry?
Who likes that?
I like that.
Meta
C++?
Fighting with meta binding.
No, template metaprogramming. So talk to me over coffee. It's anyway, it's black magic, but it's fun black magic. It's very thoroughly documented, so all the functions and classes and everything, it tells you what they do, what the preconditions are, so what you need to guarantee on the way in, what it guarantees on the way out. It cares about backward compatibility. The graphical user interface is well documented. This is all on the website. So just before I get to the actual demo, I want to talk about a couple more things. If you know Regina well, what's new in the last couple of releases? It now does high-dimensional manifolds, so there is decent support for 4 manifolds. In particular, there's a lot of algebraic machinery, which is not in the GUI, but which is available through Python and C++. It does 5 to 15-dimensional manifolds, but just the basic combinatorics of the triangulations. But if you're interested in, for instance, things like discrete Morse theory or so on, then you can use Regina for that. It's got true-width-based algorithms if you're into parameterized complexity and graph structure theory. So this is another story for another time. The first serious break in backward compatibility happened at the end of 2016. So there was basically 15 years of cruft that I wanted to get rid of, and it all got replaced as of Regina 5.1, which means that some of the classes have been renamed, but more importantly, a lot of the routines have been renamed to have rather less typing than they used to. So if you haven't seen this, there's instructions on the website to tell you how to change your scripts accordingly. All right. What's coming? Lots of links. I'll show you lots of links today, but this will be in the next release. If you want to use the machinery from the Boost Graph library, or other people's code that works with the Boost Graph library, Regina now treats triangulations and knots and links natively as 4-element graphs, which you can plug into your favorite graph algorithms to do whatever it is you need. I have a student, Alex Eastwood, who is working on code where you can give the machine a description of a problem in monadic second-order logic on a triangulation, and it will solve your problem reasonably quickly. And when I say reasonably quickly, there's an asterisk, which we can talk about over coffee. But somehow it's not, here's an algorithm, please run it, it's here's a problem, please solve it. So this is quite fun. It's based on this magic called Courcell's theorem, which comes from graph theory. But anyway, if you want to know some more, there's a website, there's a paper that's getting a bit dated now, but it tells you the history of Regina. Before I get to the demo, let me just show you a couple of things on the website, because again, so this is the website. You can download it here from your favorite Linux distribution or Mac OS or Windows. Because Regina cares so much about correctness, if there is a problem, I will tell you about it. and I will put it here. So you will see this link called Past Important Bugs. Yeah? So if you click on that, it will tell you, like for instance, there was a problem with normal surface enumeration in 2013, which probably didn't hit you, but it would have hit you if you did exactly this thing, and here's how you can tell, right? And the other one was something we picked up at ISOM, which was a problem with the large integer arithmetic. So if there are some things that might affect your computational results that you have published, for instance, you'll know about it, right? So I think this is important for having software that is designed for verified exact code. All right, demo. Let's have a demo. So here's Regina. Whoop. Let me kill it. How do I kill it? Yep. Good. All right. So here's Regina. So let's take a look at some examples. So whichever interface you're using, it'll offer you introductory examples, and that's a very good place to start. Not there, here. So you can just have a look at some 3-manifolds, some 4-manifolds, and so on. So let's pull up a 3-manifold. Here's the Poincare homology sphere. There's not much to say here. Here's the gluings of tetrahedra. You can do lots of things, right? So let's do a barycentric subdivision. Let's simplify that, right? So now we've got 120 tetrahedra. Let's simplify the triangulation. We're back to 5 tetrahedra. Let's build the vertex link as a 2-manifold. So here's the vertex link as a 2-manifold. So you can go through. Let's not do algebra. Let's take the layered solid torus. So this is a solid torus. So if you go to algebra, it gives you the fundamental group, the homology groups. You can compute your Viron variance. It'll tell you. This is all telling you about the combinatorics of the triangulation. This is doing some large-scale things, so it tries to recognize the manifold if it can. The solid torus is an easy one. It tries to find it in a census if it can, and so on and so on. Let's pull up a 4-manifold. Here's twisted 3-sphere cross 1-sphere. 2 4 simplices. Here they are. Again, you can do. So you've got elementary moves. So if you want to, okay. But because it's got normal hypersurfaces attached, so it won't let you change the triangulation because the normal hypersurfaces are relative to the triangulation. So let's clone it and change the clone. So let's do some elementary moves, right? So we can do a 1-5 move and a couple of 2-4 moves and maybe this 3-3 move and collapse an edge and so on, right? So you've got the combinatorics of wrangling triangulations. I mean, here's some of the things you can do with a 4-manifold, right? The algebra, the GUI doesn't tell you very much with the algebra, but if you go under the hood with Python and C++, you can get at proper stuff. I mean, you can get at things like the, and for the life of me, I can't remember the name now, oh God, what's the name of the matrix? It starts with an I, sorry? Intersection form. So you can get the intersection form, things like this, right? So that's not in the GUI, that's under the hood. Knots and links, let's have a look at some knots and links, right? Here's the Borromean rings, giving us 3 components with a sequence of crossings, different knot polynomials, different knot polynomials, Jones-Humphreys, Kaufman bracket. So there's not a lot there because this is very new code, but again, you haven't just got the topology, but you've got the combinatorics, so you can do Reidemeister moves and have a play with these things, right? You can simplify presentation and so on and so on. So,
where's the knot diagram?
Sorry?
Where's the
knot diagram? Please submit a patch that draws the knot diagram. I'd be very happy for that. But at the moment, it's just giving you the combinatorics. So let's do something. Let's take a figure-8 knot. Right, so let's build a 3-manifold triangulation, figure-8 knot complement, and let's do some things with it. So here it is. It's got 2 tetrahedra. You saw it in the talk yesterday. We can truncate it, so instead of an ideal triangulation, it's a proper boundary with two triangles. Let's simplify this. It can't simplify it because I promise you this is minimal, but it doesn't know it's minimal. So when you say simplify, it does some heuristics, some greedy heuristics. If it can't get there and you really want it to try harder, you can ask it to. And what it does at this point is it really somehow does a breadth-first search through the entire flip graph to try and find something smaller if it can. And if it still can't do that, it offers to go higher up in the flip graph, right? And then we'll keep doing this until either you give up or it finds something. So, so this is the kind of machinery that you've got under the hood. Jessica, that's the kind of thing we were talking about this morning. Where's Jessica at breakfast? I've lost Jessica. Anyway, okay, doesn't know. So what else? Let's make it ideal again. Look it up in the census. It finds it in 2 different censuses. It finds it in the knot and link census, and it finds it in the snappy census.
So it only checks the sensi that it has.
Sorry?
It checks the sensi that it has inside of itself.
Yes, it just checks the census inside of itself.
It doesn't like send a query to Google. So like, what is this?
No, it ships with some specific censuses. And it's,
So if someone builds a bigger census, then you'd have to get a new. You'd have to download.
Yeah. So actually, I mean, the censuses that are available are much larger than what ships with Regina because you don't want the download for Regina to be so enormous, right? So somehow there's a trade-off between, yeah. All right. Let's do something else. You can do things like drill edges. So let's build a three-sphere triangulation. Here's just a straightforward three-sphere triangulation with one tetrahedron. Let's see if there's a knotted edge, right? So let's go to the edges. Here's an edge. Let's drill this one out. So now we have a triangulation with boundary, and let's see if it's a solid torus. No, it's not a solid torus, which means that edge was not. Right? So these are the kinds of things that Regina does. Let's build the Weber-Seifert dodecahedral space. I'm not going to prove to you that it's non-Haken, but Regina does that. But what I will do is prove to you that it's zero efficient. Right? So this is a triangulation with how many? 23 tetrahedra. And what you want to do is test that there are no normal spheres in this triangulation. So you go to the recognition page, say, am I zero efficient? And it will attempt to either find a normal sphere or verify that there aren't any. And I was hoping it would do it before I finished the sentence. Yeah, right, okay, so you just make it a sufficiently long sentence and then it will finish before you stop talking. So things like this are very heavily engineered algorithms. So they are often faster than you might expect. Let's pull up the Hodgson-Weak census and do some more Hakeness testing. So here's your census. Here are some of the censuses that ship with Regina that you can actually get at as a data file. There are more censuses that it will look up, but some of them it actually ships you and lets you explore. So let's go to the Hodgson-Weak census, whereas one that I know is non-Haken. 2.35, I know this one is non-Haken. Okay, so what's it got? It's got 12 tetrahedra. This has got 12 tetrahedra. So let's run the W exponential time algorithm to test whether it's Haken. No, it's not Haken. Right? So that's an the order of n squared algorithm. Again, heavily engineered to be as fast as it can. If we pull this one up, so this is one that I know is Haken. I'm fairly sure it's Haken. Yes, this one's Haken. So let's actually see for ourselves that it's Haken. So what we're looking for is an essential surface, one with no compressing disks. So let's build vertex normal surfaces. You can have vertex or fundamental surfaces. We'll put them in quad coordinates. Off we go. So these are vertex normal surfaces inside this triangulation. There is no button that says am I incompressible, but we can do some things by hand. So let's take number 17, because I know this one is compressible. We can cut along it. So this gives us a triangulation with two components. We can extract the components. So now we can access each individual component. Let's maybe pick this one up and see if it has a compressing disk. So that's not in the GUI, but it's in Python. So let's do it with Python. You can't see what I'm typing. I can't see what I'm typing. That's interesting. Okay, item.has. Let's see how good I am. Has a compressing disk. Okay, yes, it has a compressing disk. So, but if you want to find it for yourself, you enumerate normal surfaces there. Somehow look for disks, cut along them. Right? So you can do as much by hand as you would like. Okay, so that one's compressible. This one is. Where's an incompressible surface? Number 25 is an incompressible surface. Here I'll just do it at the level of the surface actually. So let's just say item.surface.
Is B1 equals 0 for this?
Let me come back and tell you once I've, yep.
Yes.
Is incompressible. Okay, so you pull up surface number 25, say is it incompressible? Yes it is. So it's, right, so here's the Python bindings. If you are not on the iPad, then you will actually be able to see what you're doing. And today is the first time I have not been able to see what I'm doing, so that goes on to the Python list. Yeah, where's your first bitty number? Algebra. Right, so there's your knowledge group. All right, I want to just finish in my last minute with something with knots and links. So let's go back to an example list. Let's build an example. Okay, let's take the monster. This is a 10 crossing knot, which is hard to untangle. Let's simplify it. Okay. So that simplifies. So it's 10 crossings. What's so hard about 10 crossings? So let's build the Gordian unknot, which has got 141 crossings, and let's try and simplify this. As you see, it's having a bit more trouble. It got it down to 101, 97. At some point, it's going to get stuck. Right? So there's a little bit of randomness in there, so you try again. If it gets really stuck, once again, you can try harder, and this time it's searching the Reidemeister graph. It's doing a bed-first search through Reidemeister moves. It's not going to finish before I finish, so I'm going to kill that. But you want to know that this is the unknot. Here's a way to do it. Triangulate the complement. And it's built a complement, simplified it to just 3 tetrahedra, which it knows is the solid torus. So that's the unknot. Okay, I'm out of time, so I'll stop there. Yep.